A2. So A2 now, right? Reading through this, the titration of 25 milliliters of an aqueous solution containing 0.500 molar molarity of acid HA, right? So it's unknown, is performed with 1.00 molarity NaOH. HA has the following acid dissociation constant in aqueous solution. Ka is equal to 8.40 times 10 to the negative 4. So reading through this problem, we know that HA is a weak acid because it has a K value that's less than 1. So that means that what we're looking at is a weak acid strong base titration, right? Because the sodium hydroxide is a strong base. And so there are certain characteristics that we have to pay attention to then while doing any calculations for this problem, because there are different regions that are going to have different dominant species that are going to influence what the pH is of our solutions in these cases. And so one thing that I recommend doing for any of these types of problems, right, is really just, and you can do this for your cheat sheet too, right? Because you really have like the 4 types of things, but you can kind of figure out what the different regions are and how they influence what's going on, right? So, part A right here is asking to sketch the qualitative titration curve for the acid HA in these cases, right? And it's looking for us to mark then 4 different regions. One is the equivalence point. One is going to be the point where the pH is equal to the pKa. One is where the pH depends on the concentration of HA, and one where the pH depends on the concentration of the excess OH minus that we have, right? And so looking at this right here, right, if we just simply plot this, we have pH right here, we have volume of sodium hydroxide added down here, right, on the x-axis. And so what's going to happen is that when you're doing these titrations, you're going to start off at a pH, and it's initially going to go up slightly, right, because you're adding a base to an acid. And then what is going to happen is that it's just going to kind of slowly go up, right? It's going to plateau a fair amount, and then it's going to shoot up dramatically, and then it's just going to level off again, right? So kind of similar-ish shape to what we were seeing with the strong acid, strong base. The only big differences really is that the point where the equivalence point is at in terms of pH isn't going to be 7, right? So this right here is going to be the equivalence point, right? That's the halfway point between that sharp drop or rise, sorry, in this case right here, right? So this is going to be the equivalence point, and it's not going to be equal to 7 in this case, right? For no weak acid titration, are you going to have an equivalence point equal to 7? For no weak base titration, are you going to have an equivalence point equal to 7? And that has to do with the fact that now you have, a weak acid or weak base equilibrium that exists that's going to influence the pH in those cases, right? Because you're not going to be truly neutralizing something and forming water. What happens is, during the reaction, you have, where's the pen, right? The reaction essentially during the titrations, right, you're going to have HA plus, you're going to have HA plus NaOH, which is the same as just simply saying OH minus, right, is going to then react. And what you're going to end up with is H2O, which is the neutralization part, but you're still going to have some of that conjugate weak base present in the solution. And that conjugate weak base can still influence what the pH is in that case, right? Because now that's going to have an equilibrium together with the water to reform H plus or OH minus or whatever in those cases. So that's an important, thing to think about in these scenarios. So we know that the equivalence point, right, is going to be right here. We know that it's not going to be equal to 7. And, what we're going to then have in terms of the next regions, right, pH is equal to pKa. That point right there is always going to be the halfway point between the equivalence point and the start of the titration, right? It's always going to be exactly when the pH is equal to the pKa is when the concentration of HA and the concentration of A minus that you have in solution from that titration is equal to each other. And that's right, what's typically, referred to, this region right here is typically referred to as being, dependent upon HA, but it's also really easy to just simply use the Henderson-Hasselbach equation to look at it from a buffer perspective, right? Because if we think about the Henderson-Hasselbach equation, which is pH is equal to pKa, and what is it? I think plus log, I'm trying to remember off the top of my head. Yeah, plus log of concentration of A minus over the concentration of HA, right? So if these two are equivalent to each other, then that means that's log of 1. Log of 1 is equal to 0. And so if that right there is all equal to 0, then that means pH is equal to pK, right? And that's what you're going to get then at the halfway point in the titration in these cases, right? And so that's really useful in terms of trying to figure out the pKa of a weak acid or a weak base, is if you know, right, if you do the titration and you figure out what the equivalence point is, right, you can then backtrack and figure out then what the pH, at what volume the pH is equal to the pKa within that titration, and then from there, right, that they're going to be equivalent to each other, and that's how you can figure out the pKa for an unknown weak acid, right? And so that could be a kind of a problem that you might see on an exam or something along those lines. Finally, right, the last thing it's asking for is the area where the pH is dependent on the excess OH, right? That's after the equivalence point, right? So all of this right here is dependent upon strictly the OH concentration, right? Because all of the HA has been consumed. It's all been converted into A minus. And so there's still that equilibrium that exists between the A minus and HA and so forth to produce some OH minus. But compared to the amount of OH minus that you're going to be adding in to the solution from your titrant, right, it's going to be completely negligible. And so you can, disregard anything that's related to that equilibrium at that point. Right, but those right there, the four big regions really that you need to pay attention to for, the titration of a monoatomic weak acid with a with a strong base. In those cases. Question B, right? So calculate the pH after 4.25 milliliters of 1 molar NaOH is added to 25 milliliters of 0.500 molar HA. Right, and so now this is going to be the neutralization reaction. So there's two parts to calculating any of these pHs and any of those points within the titration. The first part is first doing the neutralization reaction, similar to what we were doing with the strong acid, strong base type of problems. And then once we have that, then you take those values that you've generated there, and you use those to then do an equilibrium problem in that case. And then from there, right, you get then what the concentration of H plus is, that concentration, and then you can plug that into calculating what the pH is at that point. So going through it, right, the reaction that we're doing is a neutralization reaction, right? So we're going to have HA is going to react with OH minus, and so what we're going to form is H2O and A minus in this case, right? And so if we do an ice table, right, so starting off what we have right here, right, the first thing, right, because we're doing the neutralization reaction, we have to convert everything into moles. And so in this case right here, right, we have 25 milliliters of 0.500 molarity HA. So to calculate the number of moles of HA, all we have to do now is, excuse me, do the math right here, right? So that's 0.500 moles per liter times 0.025 liters, right? So I just simply did that conversion in my head. And so liters cancels, end up with moles. So we have 0.5 times 0.025. And so what we get is 0.0125 moles of HA, right? So that's what we're starting off with, is 0.0125 moles of HA. Next, right, calculate how many moles of OH minus we're adding in. And so in this case right here, right, we have a 1 molar solution times 0.00425 liters, right? So I just simply did that conversion in my head as well. Right, so that gives us then, I don't have to plug it in my calculator, right, because it's 1 times that. So it's 0.00425 moles of OH minus, right? So you have 0.00425 moles of OH minus. We don't care about the H2O, right, because it's the solution, so that doesn't really influence it. And because we're at the start of the titration, right now what we have is then 0 moles of A minus. I know that there's the equilibrium that is occurred before that, right, with the HA on its own, right, dissociating and, going from HA to being A minus and H plus. But for our purposes right here, right, we would consider that to be pretty negligible and not influence it at all. This part right here, right, we just simply put that down as 0, just for simplicity's sake, right? It's not going to really influence our actual results at the end, especially not at this level of chemistry. So we have that right there. That's our initial. So next thing right here, right, is the change. And so looking at the HA and OH minus, right, we consider this reaction to go to completion. We can see then that the OH minus is the limiting reagent, and so that's going to be completely consumed, and so we're going to lose 0.00425 moles of HA. We're going to lose 0.00425 moles of OH minus, and then we're going to gain that number of moles of A minus, right? So 0.00425 moles of A minus in that case, right? So then at the end, what we should end up with is for the HA, we should have 0.0125 minus 0.00425. We should end up with 0.00825 moles of HA. We should have 0 moles of OH minus, and then we should have 0.00425 moles of of A minus. So we have that right there right now. One thing that we can do that is a lot easier for ourselves is because we know that we are in the buffer region essentially, right? And so the differences between the A minus concentration and the HA concentration, right, isn't anything dramatic, right? It's not like a full scale of difference. Is we can just simply use that information, and we can just use the Henderson-Hasselbach equation right now to calculate what the pH is. That doesn't necessarily always work in these titration problems, but if you can eyeball and see that they're on the same scale, right? The concentration of A minus is about half, or the number of moles of A minus is roughly half the moles of HA, right? And so that should allow you to use it as a buffer thing, right? It's not like it's a tenfold difference between the two of them. Excuse me. So you can do that. And so one nice thing too is that in the Henderson-Hasselbach equation, right, it has, as its part, right, it has a concentration of A minus over the concentration of HA. If you break that out, right, it just simply becomes then the moles of A minus over the total volume divided by the moles of HA divided by the total volume, and the total volumes cancel out. So we can just simply plug in these mole values right here into the Henderson-Hasselbach equation without having to even do any kind of conversion into molarity in that case, right, to get what the pH is. So the only thing we really have to do now is if we go back over here, right, we have the Ka value for this acid, right? We're given it right here. We have to convert that into the pKa. And so to convert it into the pKa, let me just copy that over, right? So it's 8.4 times 10 to the negative 4, right? So the Ka is 8.4 times 10 to the negative 4 in that case. And so to calculate the pKa, right, all that it simply is the negative log of the Ka. So if we take that negative log of 8.4 times 10 to the negative 4, what we get is negative log of 8.4 times 10 to the negative 4. We get 3.08 is the pK in this case. So we have the pK, so now we plug that into the Henderson-Hasselbach equation, right? So the pH is equal to the pKa, what is it again? I can't remember off the top of my head. I know for exams, you'll have the cheat sheet. I would always recommend putting it on there, right? So you have the plus log of the concentration of A minus over HA. And so we take that, excuse me, and plug in our numbers, right? So we have 3.08 plus the log of 0.00425 divided by 0.00825. And so the pH is going to be equal to 3.08 plus the log of 0.00425 divided by 0.00825. And so you get a pH of, where's my thing, of 2.79, right? Which I believe is what I have on the key. 2.80, yeah, same thing, just rounding difference. Right, and so you get that right there. If you were to go through, right, and do, the conversion of everything to doing it with, an ice table and all of that stuff, you should get the same result, right? So if I just go through right now and I do that, so if I convert, so the total volume now, 4.25 and 25 milliliters, right? So, excuse me, 0.00425 divided by 0.02925, right, gives us 0.145 molarity. Do that same calculation for the HA, right? You get 0.282, right? So that's, again, it's about half in that case. So I have those, right? And I have in the equation, so I have K is 8.4 times 10 to the negative 4. If I do, do the assumption that the 5% rule, right, doesn't really have an influence, excuse me, in this case right here. And so if I write that out, right, Ka is going to be multiplied by the concentration of HA, so that's 8.4 times 10 to the negative 4, right? And so then you have up top, I should just write it all out. Right, so we have Ka is equal to H plus A minus over HA, right? And so you have X times 0.00425 plus X divided by 0.00825 minus X, and then that's going to be equal to 8.4 times 10 to the negative 4. And so then what you get is, right, if I assume that this right here doesn't matter, you get 2.37 times 10 to the negative 4 is equal to 0.00425x plus x squared. And so then now, right, if I use the quadratic equation, so we have x squared plus 0.00425x minus 2.37 times 10 to the negative 4. We solve for this, we get 0.0134 in this case right here, right? And so we do the 5% check, right? So 0.0, that can't be right, because the concentration of X now is greater than what the other concentrations are. So wait, did I mess something up? I had to have. Wait, no, sorry. Right, because I had 0. This number is off. This is what I get for trying to speed my way through it. I put the moles, I didn't put the concentrations, right? So this was 0.145 plus x, and then this was 0.282 plus x in that case, right? So this becomes 0.145. So now solver, right, x squared plus 0.145x minus 2.37 times 10 to the negative 4. And solve for this, what we get is x is equal to 0.00161, which is a much more reasonable number in my mind. Right, so we get that right there. And so then if we take that number, so take that, divide that by 0.282, right? It's slightly above, no, actually it's 0.005%. So, or 0.5%, sorry. Right, so it's not outside of the 5% rule, so we don't have to worry about that. In this case right here, right, so the Henderson-Hasselbach equation will work, right? The conversion, right, using the simplification will work. And so if we have that, so the negative log of that number is 2.79, which is what I got right there using the Henderson-Hasselbach, right? So I just did a whole roundabout way of basically proving, right, that the Henderson-Hasselbach equation can be used in this case, right, and that it's a completely valid way. And it's a much faster way to do a lot of these titration problems. The only times really that you have to worry about that not working for you is if the solution is incredibly dilute, or if the ratio of the acid and the conjugate base, or right, the base and the conjugate acid, if those are really, really, off, right? So if, anything that's, a tenfold difference, is going to influence it in that case. But in this case right here, right, we didn't have to worry about that. So that's the easiest way to do those, right? It's a pretty quick way to do it. It's a lot faster, right? As you saw, it took a little bit more time, right, to go through the proper equilibrium way to do it. And I didn't even do the whole way, right? I didn't do the ice table. I didn't do any of those things, right? Because, just from experience, I know how to do those. And I only did that really just to prove the point that using Henderson-Hasselbach is completely valid and you get the exact same result. It's just that it's a lot faster in that case, right? And so that's a thing to always consider, especially on an exam, right? Just as a tip for an exam, it can always take a long time to do certain things. And so anything that you can think of that will help speed it up by using either an equation that already has a whole bunch of things contracted, or, constants that, you've already pre-calculated beforehand that, you're going to be using over and over again, like, in the case of quantum when we were doing that, or even in terms of thermo, those are always going to be, a pretty good thing. So for titrations, right, if you're in the buffer region, there's a pretty good chance you're going to be able to use the Henderson-Hasselbach equation. The only time you really wouldn't be able to properly do that is if you were working with something that is incredibly dilute. But that probably won't be the case. But who knows, right? I'm not writing the exam. All right, so pH is 2.79 at that point in the titration. Next, calculate the pH after 12.5 milliliters of 1 molar NaOH is added to 25 milliliters of that, right? So again, now what we're doing, so the way that this problem is worded is slightly different from how problems were worded for other things. At this point right here, right, now we're adding 12.5 milliliters in total, right? So we're not adding it on top of the 4.25 that we have right here, right? What we're doing now is adding it, to the system as a whole right there. So we have, again, we set up our neutralization reaction, right? So we have our HA, we have our OH minus, and we're going to form A minus and H2O, right? So initially, in terms of HA, right, we're starting off again with the 25 milliliters of 0.500 molar HA. So we can just start off with that right there. So we're again at the beginning of our titration. So we have that, right, for A minus, right, we have 0 right here. And now for H minus, right, now we're going to be adding 12.5 milliliters of a 1 molar NaOH solution. So we can calculate that right here real quick. So, right, so in terms of the number of moles of OH that we're adding, that's going to be equal to 1 molar, right, which is moles per liter. Multiply that by 0.0125 liters, right? So I just did that conversion of milliliters to liters in my head. So liters canceled, we end up with moles. And so what we end up with is, right, because it's just simply 1 times that, we end up with 0.0125 moles in this case. Right, so what we have now is 0.0125 moles of OH minus that are present. Right, now we're looking at the change, so we're looking at what's the limiting reagent going through it. Right, they're both equal to each other, so they're both going to completely neutralize themselves, and so we're going to end up with consuming all of that. So it's 0.0125. Right, both of those are going to be lost, that many moles. And now A minus, right, is going to gain that many moles, right? So 0.125 moles, right? So plus in that case. So in the end, right, we'll have 0 moles of HA, 0 moles of OH minus, and then 0.0125 moles of A minus. Now, right, we're at the equivalence point in this case right here. The equivalence point for a weak acid, strong base titration is not equal to 7, right? Because, as we can see right here, right, we have now a fair amount of that weak base that's present in the solution, and that weak base now can undergo an equilibrium together with water, to form H plus and OH minus. And so at this point right here, there is no shortcut, right? We actually have to go through and do the equilibrium, acid base problem, right? So we have this right here, and so what we want to do now is just simply convert that into a concentration. So we want to get the concentration of A minus, right? So that's going to be 0.0125 moles divided by, right? So now the total volume is 12.5 plus 25. So that's 37.5 milliliters. So that's 0.0375 liters. So we take that, we have is 0.0125 divided by 0.0375. And so what we get is concentration of 0.333 molarity, right? So we have that. So we have that concentration. Now, what the problem now gets turned into is being a weak base dissociation, acid base problem. So now we set up our new reaction. That's the dominant reaction that's present in the solution, which is the reaction of A minus, right, with water to form HA and OH minus, right? So it's the weak base dissociation reaction now. So we have that, right? So we set up our ice table, right? So initially we're starting off with a concentration of 0.333 molarity of A minus, right? H2O, right? None of that matters, right? Because it's the solvent, it's a liquid, it's not part of the equilibrium. HA, right? We consider that to start off being at 0. OH minus, right? We consider that starting off to be at 0. So now, right, change is going to be minus X in this case for the A minus, and it's going to be plus X for HA and plus X for OH minus. And so then at the end, what we have is 0.333 minus X, and then X and X in that case. And so now, right, what we do is we set up the equilibrium expression. So this right here is a base dissociation reaction. So that's going to be Kb is equal to the concentration of HA times the concentration of OH minus over the concentration of A minus. So we plug in those numbers, right? So we're going to end up with X times X up there, right? And that's going to be divided by 0.333 minus X. Now, we're looking at the Kb. We were given the Ka, right, in the problem. The Ka and the Kb aren't the same. However, we can convert them from one into the other. And the way that we do that, right, is that we know that the relationship between the two of them is going to have to be Kw is equal to Ka times Kb, right? That's the relationship between the two of them in those cases. And so if we, rearrange everything right here, right, what we get is Kb is equal to Kw over Ka. And so the Kb then becomes, right, so it's 1 times 10 to the negative 14 divided by the Ka that we have, which is 8.4 times 10 to the negative 4. So that gives us then that the Kb is 1.19 times 10 to the negative 11 in that case, right? That's what the Kb value is. And so that's what we're going to use down here then, right? So 1.19 times 10 to the negative 11. And so we can go ahead and just do our 5% approximation at first, right? We just simply consider that, right, to not matter. And so what we then get, right, is then going to be x squared is equal to, what is it, 1.19 times 10 to the negative 11 times 0.333. And so what we get is 3.96 times 10 to the negative 12 in that case. And so now, right, we take the square root of both sides, and so what we get is that x is equal to 1.99 times 10 to the negative 6 in this case right here, right? So that's our concentration then of OH minus in solution, right, from that right there. So we know what the concentration of OH minus is, right? We can use our modified equation to figure then out what the pH is by going through the pOH, right? So we know that, let me just, right, we know that the pH is equal to 14 plus the log of OH minus. And so if we plug in our number here, right, we have 14 plus the log of 1.99 times 10 to the negative 6. And so what that gives us is a pH of 8.30 in this scenario, right, which is what I have on the key, right, 8.30. So that's how you calculate the pH then right there, right? So that's what, at the equivalence point, right, that's what the pH is. And again, the equivalence point is when you have fully neutralized the weak base, or sorry, the weak acid by the strong base in this case, right, when they're stoichiometrically equal to each other. And in a weak acid, strong base titration, the equivalence point is always going to have a pH that's greater than 7. In a weak base, strong acid titration, the equivalence point is always going to be less than 7 in those cases, right? Because at that point, the dominant species becomes the conjugate in that case, right? And so if you're the dominant species is the conjugate base, you would expect it to be a more basic solution compared to, pH neutral, right? pH is equal to 7 in that case. So again, right? So it's a little bit more of a little bit more work in that regard, but that's how you get to that point right there. Cool. Yeah, and so that's all of A2. Now, if you wanted to, right, if you were going to go on, and so I would recommend, actually, I'm not going to go on and really ramble about it. I have other videos that I've posted, especially ones that I've posted to YouTube that I have on that on the page, right, where I actually go through a lot of different types of titrations and I go through a lot of different points within the titrations and talk about them. So if you want to see, what it looks like when you are calculating it at the equivalence point, or sorry, not the equivalence point, right past the equivalence point, or if you want to look at it for, I think I also have a weak base, strong acid titration up as well, so you can see what that then looks like. But the process is pretty much the same. You always, for these titrations, for a weak with a strong, you always first do a neutralization reaction to figure out how many moles of the weak acid and its conjugate base you have present in solution, and then you go through, and in many cases you can use the Henderson-Hasselbach equation when you're in that pre-equivalence point region. Sometimes you can't, right? Again, there's always going to be that 5% rule that you have to pay attention to, but you can do that, and then when you're at the equivalence point, right, you see that flip for just a moment, where then now the conjugate base in this case right here, right, is the dominant species, and so then you have to go through a different approach for calculating the pH. And then once you're past that point, right, at that point it just simply is completely dependent upon what the concentration is of, or the amount of OH minus that you're adding in that case, right? Because looking at this right here, the concentration of sodium hydroxide that you're adding, right, it's 1 molar. So even if I were to go add 1 more milliliter past this point right here, right, what I'm essentially adding is 0.001 moles of OH minus to that system, and that starts to then overwhelm, what's going on in terms of this equilibrium right here, anyways. And so, that equilibrium becomes completely irrelevant, and it just, blows right past it, and the pH is then just completely dependent upon the OH minus concentration. And all you have to do is just really recalculate what the concentration is in its new volume, right? It's not because that's going to slightly change, but yeah, so that's what you have right there for that.